Okay, now to get a gist of what simultaneous does not necessarily mean simultaneous and length contraction. Suppose we have this person inside the spaceship and his equidistance between the two ends of the spaceship. So his equidistance between this point and this point. So let's say if the person is equidistant between these 2 points in the spaceship, and let's say lightning strikes simultaneously, like two simultaneous lightning strikes at this point and at this point. So the observer here inside the spaceship, he would see this lightning, he would see this lightning propagate. He would see this lightning propagate first, then this lightning, because he's moving in the direction of the propagation of the lightning. So let's say the lightning propagates like this. The lightning propagates like this. Observer here will see this lightning first before he sees the lightning propagate from this end. The observer would see this lightning propagate first before he sees this lightning propagate first. But then wait, hold on a second. The speed of light is the same in all reference frames. The speed of light is the same in all reference frames. So how can this guy see this light first before he sees? How can he see the front light come first before he sees this light? Well, we say that if the velocity of the spaceship is moving relatively close to the speed of light, we say that we say that as seen by this observer, that the length of the spaceship changes and it contracts. So let's say uh this was the initial length. So let's say this was the initial length. When if the spaceship contracts, then the observed length would probably be this. Would probably be this. This is what it means to length contract. And then now to get a gist of simultaneous, not necessarily simultaneous. Well, this person, the observer, when these two lightning strikes, he sees the lightning strike simultaneously. But then this observer, he sees this lightning strike first and before this lightning strikes, because he sees the light come from this lightning first, then he does see the light come from this lightning. So based on your reference frame, you you may or may not see simultaneous. So simultaneous itself is relative. So this is very amazing to me. Einstein proved that simultaneous is relative. Simultaneous is not necessarily simultaneous. It's just simultaneous based on your own reference frame. That's kind of really cool, man. I think that's mad cool. So, uh, yep. Something that I forgot to mention that's really essential to this modern physics stuff is that there's no absolute frame of reference. There's no favorable frame of reference because everything is moving with respect to each other. The 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 Earth is moving with respect to the sun. The planets are moving with respect to the sun too. The sun is moving with respect to the galaxy. The galaxy is moving with respect to the whole universe. Everything is moving. Everything is moving. So there's no absolute frame of reference that everything can be measured by. Everything is relative, and every frame of reference is relative. Now, if we say that the original length, which is the length measured by this observer when the spaceship is stationary, is related to the contracted length by the contracted by gamma. So gamma times the contracted length equals the length of the initial. Is the length of the spaceship stationary to the observer. Now suppose you have two twins, Tweedledee and Tweedledum, and Tweedledum is the one who will go inside the spaceship. So let's say Tweedledum goes inside the spaceship. You know, he goes inside the spaceship. He goes inside the spaceship, rides on the spaceship with fast speed. You know, speeds close to the speed of light, and then he comes back. He comes back. Well, Well, in Tweedledee's perspective, Tweedledee's, I mean, inertial frame of reference, this this guy is moving with speed. Tweedledum is moving with speeds close to the speed of light, which means that time will slow down for him, and then in his perspective, time will like go fast for him. So when Tweedledum comes back to Tweedledum comes back, Tweedledum comes back, then Tweedledee will seem to be older because time went by faster for him. So if Tweedledee comes back, this guy, let's say, would have, I don't know, a beard. Like this guy would have a red beard. Yep, a red beard. And this guy would have like only a small beard. So basically, this guy, Tweedledum, will will be in his perspective, in Tweedledee's perspective, he would age much more than Tweedledum. But in Tweedledum's perspective, so in Tweedledum's perspective, he he remains stationary. If the spaceship is moving with constant velocity, he remains stationary, and Tweedledum was the one moving. So Tweedledum was the one whose time slowed down and his time went faster. So in his perspective, in Tweedledum's perspective, this guy is much younger than he is. This is a famous paradox. Is I don't think it could be proven. I'm not sure, but it's a famous paradox from Einstein's relativity. Okay, is but so we learned from before that there's no absolute frame of reference in which everything could be measured by. So in analyzing the momentum of like these two balls, like the spaceship throws this ball and then the spaceship throws this ball, we could analyze this momentum in any frame of reference in which we choose to. So we could analyze the momentum, let's say, in the spaceship's frame of reference. So say that we analyze the momentum in this spaceship's frame of reference. Then in this spaceship's frame of reference, time is moving faster than in this spaceship. That means this spaceship is moving with a higher velocity than this spaceship. So if that's the case, then supposing that the two balls have the same mass, we could say that an observer inside the spaceship would think that would see that for him in his frame of reference, he's gonna think that the spaceship time is being slowed down in the spaceship. So as a result, this ball, like when this ball is released from the spaceship, he thinks that this ball is also moving with with time being slowed down as well. So he thinks that this ball is moving with a less velocity. So in his perspective, he thinks that there's no way that the red ball will keep on going this way in this path. He thinks that the red ball will obviously move in the direction of the yellow ball that he's throwing. But then, is this the case? Let's say when the two balls meet up at this point, each ball, like the red ball, moves this way back to its original spaceship, and then the yellow ball moves this way back to its original spaceship. So, how's this? From this frame of reference, from this spaceship's frame of reference, he doesn't think this can possibly happen. It's impossible for him, because in his frame of reference, time is completely being slowed down in the spaceship. So there's no way that the spaceship will have enough momentum for it to resist the momentum of the yellow ball. It resists moving in the direction of the yellow ball. So he thinks this is not possible. So how did this case even happen then? If that's the case, well, even though this observer views time as being slowed down in the spaceship is still moving with a really high velocity. So since the spaceship is moving with a really high velocity, that means the mass that made this ball move back to its original spaceship, must come from the speed that it's moving in with that's the speed that it's moving with this high velocity spaceship of that. So so it turns out that this mass is increased by a factor of gamma, which is equal to which is equal to which is equal to 1 over 1 minus v squared over c squared. So as we can see, if the mass is increased by this factor of gamma, that means the momentum is also increased by a factor of gamma. Now, if this ball's momentum is increased by a factor of gamma, that means its energy must also be increased by a factor of gamma. So we could write this. Now, this clearly shows us that the higher an object moves closer to the speed of light, the greater it would gain mass, the greater the mass it would have. So if that's the case, then and this could clearly be shown in this equation, because if this bottom part of the equation, if v in this bottom part of the equation equals the speed of light, that means this bottom part of the equation would be 0. So you have 1. So you would have gamma equals 1 over 0. And if gamma equals 1 over 0, 1 over 0 is approximately infinite. So you would have infinite mass. And infinite mass is not possible. So that clearly shows that nothing could move at the speed of light. So if photons are moving at the speed of light, how come they don't have infinite mass? Well, photons don't have mass at all. So that's why. Lastly, I will mention the notion of space and time. So what we must first understand is that since light is the same for all observers, and light itself is affected by gravity, that means gravity must affect the way time flows. Yeah, that means gravity must affect the way in which time flows. Now, if gravity affects time, that means if gravity affects time, and that means there must be a spatial dimension in which both gravity, time, and like space and time are unified together, and this is what scientists call this space-time fabric. Like the unification of space and time as a separate dimension is called the fourth dimension. Another thing that Einstein mentioned was that space itself is like gravity could be thought of as a curvature of space and time, and this just shows, and if gravity is the curvature of space and time, this the curvature will affect the planets to rotate around it, and this is basically a perception of it, like a video that demonstrates this. And then basically, if you have a black hole, and then since a black hole is the infinite curvature of space and time, that means time itself stops, time itself stops in black holes. Okay. As can be seen here, you see the black hole, it's an infinite curve of space and time, while the sun is, it's not an infinite curve.